Okay, everybody, welcome back. Let's see if we can get through our talk without mentioning turtles this time, or maybe we mentioned turtles. It's okay. Our next speaker is well known to the Hackaday community, having presented at every con we've had so far. If you were lucky enough to attend the 2019 con, the conference badge that everyone got to play with was his design. Today he's going to take us on a journey beneath the plastic blob, covering a chip on board device, and show us just how hard reverse engineering an unknown chip can be. You probably know him better as Sprite TM, but please welcome Jeroen Domburg.
So hello everyone. Yeah, I think everything should be set up now. Okay, thank you, Dan, for this great introduction. So what we're going to do today is look at the mysteries of this particular piece of tat. This is, well, we call it a Buddah flower. It's actually a meditation aid that you can buy on the internet in order to help you meditate. And what it does, it actually, if you turn it on, there's electronics inside. Obviously, there's electronics inside. It plays music, it plays Buddhist chants, both to help you meditate as well as something that here in China you can put next to when someone has died. You have effectively an automated prayer machine. And let's see if I can get to my presentation. Sorry, it's still early here. I'm very not in a multitasking mood. Okay, obviously the question is, why did I get such an obvious piece of tat that is of a religion that I'm not even like a member of? Well, it all started with the YouTube channel bigclive.com. You probably all know it, and if not, go and watch it. And he had this Buddah flower. He got it off AliExpress or something, and he was interested in what makes it tick. And so he opened it up, and what's in there is effectively a little PCB that runs the entire show. And obviously there's also a bunch of LEDs and a speaker in there. But the most important part is this little PCB. So what's actually on the PCB is a 2 megabyte SPI flash chip, which is just a Jelly Bean part, and probably the songs are in there, we assume. And the other thing is a so-called blob, a chip on board, a bare piece of silicon that has been bonded to the board and is, people put some epoxy over it and they call it a day. However, that flash chip is interesting because that is very common and you can dump that and you can reprogram that. So the question he asked was effectively, would it be possible to replace the songs on this flower for something a bit more, Western maybe? So obviously the entire comment section of the YouTube video immediately went to look at it. My presentation is not doing what I wanted to do. Hello, what are you up to? My keyboard is running away from me. I have no idea what that was, sorry. We got a file called buddha.bin, which is 2 megabytes exactly. Obviously everyone ran the usual suspects on it when it comes to inspecting what firmware does. So you start off with the Unix program file, which happily tells me it's data. Thank you, Captain Obvious. Binwalk, which is usually very good at finding stuff, finds absolutely nothing. And even strings can't really find anything human readable in the binary. So Binwalk has an entropy view, which effectively tells you over the size of the file how random it is. And if it's more random, it either means that stuff is encrypted or stuff is compressed. You unfortunately can't really see the difference between the two. And what you see here is that most of the time, the entropy is very high. So it's either compressed or encrypted. There's only a few tiny little blips where the line goes up to a level that is not like very close to 1. So obviously with all automated tools failing, we still have one remaining tool, and that is to just look at the hex data. And what we see here also doesn't quite make sense. I mean, you can see that there's some pattern to it, But if you look at the hex values, there's not really anything in there that seems to stand out. And a little bit later in the other low entropy section, there's more of the same. You can see it repeats, but what all these individual things mean doesn't really seem to make any sense. And even later in the large high entropy section, it just becomes gobbledygook, and there's no pattern that we could discern in there. So, you know, sometimes you just have to stare at these things for long enough and just simply hope for enlightenment. And if you do that on this code, you can kind of start seeing something. There's a certain pattern that is emerging. You can see the pattern, but there's nothing really that stands out. You know, I think this is something. This is shitty encryption. Okay, so I need to qualify that. What is shitty encryption? Well, there are certain levels of encryption. You've got your old standard alias encryption, for instance, and all the other proven and reliable and tested encryption methods. And these are effectively, if well implemented, these are bulletproof. As in, you put in a key, you put in a short string, you alias encrypt that, and you get gobbledygook, and without the proper key, you'll never get that string back. However, you can also implement it badly. There's a very famous image of a picture that is encrypted using this method. And you probably can't tell what this picture originally was because the encryption, you know, makes it into gobbledygook, right? Right? Anyway, then you have encryption that people just made up. Like you had a programmer and they were like, oh, this sounds like a few very good routines. And if I run this on my code, then no one can ever figure out what it is. So this is what that would look like. You take hello, you decrease all the bits by 1, you flip all the bits, you bitwise invert it, and then you reverse the entire sequence. So whatever programmer came up with that might have thought that it was a very good idea, might have even sung about it. But yeah, if you know a little bit about cryptography, you know that this can be broken pretty quickly. And finally, you have when they don't even try. This is called obfuscation. And obfuscation is effectively used if you don't want people to see immediately what it's on about, but you don't really care if they break the scheme or not. So another definition of shitty encryption, or at least where it comes from, is a very nice quote by Bruce Snyder. Anyone from the most clueless amateur to the best cryptographer can create an algorithm that they themselves can't break. And this is kind of what I think happened here, maybe. And in order to show how it works, I got to tell a little bit about XOR encryption. If you already know this, this is only going to take a few slides. So if I take the text hello Remoticon people and I do XOR encryption with super secret key materials, what effectively happens is that I take every byte in the original text and I XOR it with the corresponding byte in the key. And what you get is, again, gobbledygook. However, if I take a different string that is changed only a little bit, it now says hello Hackaday people instead of hello Remoticon people. And I encrypt it with exactly the same key. You actually get something interesting because this works on a byte by byte basis. The first and the last bit of the encrypted data are exactly the same. The middle bit is different, obviously, because the text there is different. But the first and the last bit are the same. And if I only have the plain text, I can tell that, you know, probably the data in those locations is exactly the same. And there's a second property. And that is if you XOR encrypt data that is all zeros, your result effectively is the key. So you should make sure to never do that because you can just read the key straight out of the encrypted data stream. So too long didn't read is if you XOR data with a key, you get gibberish. Something that I didn't mention, but is true, is that you XOR it with the key again, you get the data back. Both the data and the key kind of leak into the gibberish. And yeah, you should never try to encrypt all zeros. With that in mind, if we go back to the binaries, something interesting pops up. And if we take the other region and also look at that, then, you know, more interesting stuff pops up. And a little bit later, you get even more interesting stuff. So strangely, all these things, for instance, start with EFFF, and these are all structures. They're either 32 bytes or 16 byte structures that describe something. And a value you often get in structures like that is all zeros. So it's very likely that of these structures, a whole bunch of them start out with all zeros, which means that we now know the first two bytes of our key stream, which is likely EFFF. So a whole bunch of us started working on that, and we recovered the key stream. It's EF, FF, DF, 9F, 1F, 3E, 7C, F8. Oh, this goes on forever. Yeah, this doesn't repeat itself. So there must be something that generates this. And we can actually figure this out pretty easily, because if you see how the XOR key changes from byte to byte, you see that EF, for instance, only goes to FF. 9F only goes to 1 out of 2 values. F0 also goes only to 1 out of 2 values. There's no third option. And in general, if you look at these values hard enough, you can figure out that if you have a certain previous XOR value X, then it either becomes then it either becomes the value left shifted by 1, or the value left shifted by 1 XORed with 21 hexadecimal. So here's that routine in C, if you think it's easier to read that. But the trick is that it's dependent on a certain bit that is generated somewhere else. That bit decides which of the two values to use. And obviously, because we have the key stream, we can also look at what those bits must have been. And you get this range out of there. And the issue is that, again, it goes on forever. And in this particular case, there's no real pattern discernible in there. It kind of looks like random. So again, there's not much to do here with our tools. We have to just, meditate on this a bit. And then you start thinking, like, this looks random. So first of all, it must be generated. So there must be some generator in there, and it looks random, but it is repeatable. So maybe this is a pseudo-random number generator, seems likely. So what kind of pseudo-random number generator would you implement in a small chip? Well, it must be a linear feedback shift register. It's just about the cheapest way to implement a pseudo-random number stream. So linear feedback shift register looks like this. The top bit is hardware. You effectively have 16 flip-flops, or a certain amount of flip-flops. And they form a shift register, but every now and then there's an XOR inserted that XORs the value with the last flip-flops value. And the bit under it is how you would implement it in C. So LFSRs come in a few different sizes. So there's a few unknowns. We don't know the length of the LFSR, so how many flip-flops are involved. We don't know the position of the tabs, so where the XOR gates are inserted. And we don't know what the initial state of the flip-flops are. Well, we can guess a few things. So the length of the LFSR we can guess. It's probably a multiple of 8, because that's common. And it's probably not 8, because that's a little bit on the low side. So that's likely 16-bit. Tab positions we don't know. So, there's 2 to the 16th possible tab positions we need to try. The same thing is true with the start states. There's 2 to the 16th. So that means that we've got 4 billion options to go through. And you might think like, oh, that's a lot. It's not. LFSR is really small and quick to do. So on my 5-year laptop, I can burst through that in 60 seconds, even less. So whipped up some code, and that code ended up being a encryption brute forcer. So I now have a program that does everything described above automatically. So you feed a binary into it, and it gives you the keys. So that results in effectively the binary is now fully cracked, and you can see stuff show up. And this actually looks like a file system of sorts. And that's true, it is a file system. And this is what it normally contains. You've got a file called code.app, which is a file which has its own internal segments. And then you've got a whole bunch of files called something.f1a. So the stuff in the code.app is, well, code, as it says. And the stuff, the F1a stuff must be audio, because it's effectively covering the largest part of the flash space. And there's just as many in there as there's supposed to be songs in the thing. So we now have machine code, but what CPU is it? Well, you actually have tools for that. And CPU rec actually tells me it's an 8051. Okay, so an 8051, I had a whole section here detailing the ins and outs on it. I have a few opinions on it. I'm not gonna get into it. I don't want to make this too opinionated, but so just let's skip over this. The truth is we do have an 8051, and we can now see the disassembly of those overlay chunks in the code.app thing, which is great. I mean, we've got code to look at, and because this is in Flash, we could even, replace this code with something else. However, the thing is that the code is unfortunately incomplete. So why is it incomplete? Well, not all the code is in Flash, and there's a few reasons we can deduce that. Well, first of all, the code.app is only 9K of size, which seems a little bit on the small side. The other thing is something needs to load the code.app. Something needs to do the decryption and figure out where code.app is, and that is likely some other code. And the most obvious smoking bullet is that the code.app has calls and jumps into some memory region we don't have yet. So up till now, we've done everything just using the 2 megabyte Flash binary dump that Clive made. But now it's time to actually get our own Buddah flower. So I got one of Taobao. It cost me like, this is the equivalent of like $7, I think. And yeah, I received it. It looks exactly the same as Big Clive's. Only mine has 56 songs. Here are all of them if you're interested. And obviously I opened it up. It looks pretty much the same internally, but the PCB is a little bit different. I don't get a blob. I actually get a proper 16-pin chip. Unfortunately, the chip is not marked anywhere, so I still don't know what chip this is or who makes it. Well, never mind. We have something to do. We actually need to figure out what the data in the unknown sections in probably the ROM of this chip is, and we need to get it out. Well, reading it out is not that hard because we can just replace one of the overlays with something that reads out the data. But how do we get it to a PC? How do I get the binary on my hard disk? Well, that's a bit of a problem because I didn't see a UART anywhere. If I scoped around, I don't see any serial signals. There's one button GPIO there, but that's input, and I have no idea what the chip is, so I can't turn it into an output. I actually checked. There's common peripherals for an 8051, but this one doesn't seem to match that. So maybe the SPI. Maybe if I poke around, I can just find the SPI data register, and maybe that's enough. An SPI would actually work great because this is a quick sketch of how the thing, how the PCB works. So you've got the mystery chip and the flash chip, and they're connected by an SPI bus. And how an SPI bus normally works is that you pull the chip select line low in order to indicate to the flash, hey, I'm going to do something. And then you communicate it over the data and the clock lines. However, if you communicate over the data and the clock lines when chip select is high, the flash chip is effectively deaf. It'll ignore that little bit of communication. So if we can, trick the mystery chip into doing that, we can just, connect a logic analyzer to those pins and then read that ignored data into the PC, decode it, and, we can communicate with our dumper. So yeah, let's do that. So read all the memory. So it's very simple. We take the flash image, we unpack it, we replace one of the overlays with our dumper program that just reads the memory and pushes it to the SPI data register. We repack the flash, we program the flash chip, we resolder it, we attach our logic analyzer, power the entire thing on, dump the SPI traffic, and we've got our binary. Awesome. So that actually works. And now we got to look at what the binary is. And luckily, one of the good things that the NSA has left us is Ghidra, which is an awesome tool for reverse engineering stuff. And it also understands the 8051, so we can happily reverse engineer this. And this is what that looks like. So you've got a nice disassembly. Ghidra also does a brave attempt to convert it into C code, given the fact that half of the code isn't even written in C. That's pretty interesting. And one of the things is we can now explore the chip a little bit more. For instance, we can figure out what the memory space looks like. So this is the memory space of the chip. You've got 4K of RAM here. You've got 8K of very clear, obvious ROM routines here. You've got a mystery region here, which is 8K. I'll come back to that later. And but let's first focus on the RAM. So because the SPI flash code regions are actually executed from here. And the reason I call it overlays is because they actually work like that. And the way it works effectively is, say overlay 0 is in RAM and it wants to call a function in overlay 2. What actually happens is that the compiler inserts a call into ROM instead. So overlay 0 will call into ROM, and ROM will use the SPI peripheral to load overlay 2 into RAM. So it entirely overrides the calling code. It'll then jump into overlay 2 and just execute whatever function it is. And as soon as it returns to ROM again. And the ROM will reload overlay 0 and execution will happily continue from there. So it's a pretty interesting way of doing things. But hold up, there was a region that has a big question mark. What's up with that? Well, if you go into Ghidra, you see this. Ghidra detects that there are subroutines here because there's other codes jumping to this code. But the memory region reads as all zeros. So they're trying to keep something from us. Seemingly this ROM is not readable. So we got to make sure that we also have this, because obviously we want to have access to all the code that's in this chip. So the idea of the secret ROM actually reminded me of the Game Boy Advance. It has something pretty similar. If you look at a very simplified memory subsystem structure of the Game Boy Advance, this is what it looks like. And the trick is that if you want to read the ROM memory from the cartridge, you can't. If you want to read the ROM memory from RAM, you can't. Nintendo actually designed the hardware to stop you from doing that. The only thing that can read from the ROM memory is code running in the ROM itself. So you need to run your code from the ROM in order to read the ROM. But obviously you can't just stash your own code in ROM because it's read-only memory. So in order to read it, what the people reverse engineering the Game Boy Advance had to do is find a routine that could be abused in order to read from the ROM and then return data. And Nintendo obviously is not a big fan of this. So for most of the routines in ROM, they actually check if you're trying to do something with an address that itself is in the secret ROM, and they will just return 0 then. Except for one function. There's one function that you can actually feed a pointer into ROM and it won't check that. And it returns a certain value that you can demangle to whatever byte was at that certain ROM pointer thing. So now we need to find something similar in our chip. And obviously hope that they don't, that they're smarter than Nintendo and do we got to hope that they're not smarter than Nintendo, so they don't check every pointer that goes into that. Obviously, we have no idea in this case what the ROM functions do, so I just picked one as random. This is a bit of code that I do have that calls a ROM function that lives in the secret ROM. I have no idea what it does, but it looks good because you can actually see that it that one of the arguments is a pointer into the non-secret ROM, so maybe it can also do something with the secret ROM, who knows? So literally first function I grabbed, and I actually was lucky because yes, a side effect of that function that's called is that the accumulator register gets filled with the memory at the D pointer plus 3 bytes. Which is awesome because it means that I can just run that with the D pointer pointing at the entire secret ROM range, and I'll just get the secret ROM, which is great. And then I had the secret ROM, and I was actually curious, what does this routine do? Like, what was the way that me calling this and reading the accumulator snuck past all of their defenses? I mean, maybe they just maybe they just overlooked the fact that there was a side effect that the accumulator got used and then not cleared. Well, actually, no, the function does a plain memory copy of 4 bytes. There's no checks at all. I could even read the ROM if I used this function like the way you should. So yeah, this is a great example of the hardware guys making stuff secret and then the software guys messing it up entirely. So we now have all the secret routines as well, which means that we have, to my knowledge, all the code that runs in this little chip, which is great. But unfortunately, there are still no clues to who makes this chip in there. The ROMs doesn't contain any strings or any other stuff that makes it very obvious. So, however, at this time, obviously, I wasn't the only person who wanted to have their own Buddah flower. So someone else, Neil555, also ordered his, and he got it. And his PCB was different again. So he doesn't get a blob, and he also doesn't get a nameless chip. He actually get a chip with silkscreen on it. So this chip is made by a company called Geely. It is, if you have a cheap ass Bluetooth headset, it's very likely that their chip is in there. And obviously, like the PCB is different, the chip might be different. They might just have switched manufacturers, and this might just be an entirely different chip. So there's actually a way to find this out, because there was a ROM dump provided of the flash chip in this on this PCB as well. And I can just feed it into my brute forcer, and my brute forcer happily found the key materials, and I could happily unpack this flash binary. So yes, it's exactly the same chip. So now we know which chip it is. But as you probably know, if you only have a type number and you throw that into Google, you're not likely to get results for obscure Chinese manufacturers. So one of the tricks you do then is you just take the name and you just backspace the last characters until you get a hit. And we actually did that. And a familiar person popped up. So Foon, they twittered about this a while ago. And it's a chip with similar markings. The last bit doesn't match, but the first bit does. And he actually found this on a cheap MP3 player PCB. And he and his Twitter fans did some research, and it's actually something with an 8051 core. They found a datasheet, and they also found a name. It's often called the AC1082. So hey, this is a lead, you know. If this has an 8051 and is publicly known, then maybe there's also an SDK out there. You tend to have these obscure websites where people just upload all sorts of private stuff like SDKs and stuff. They're usually like obscure Chinese or Russian sites. So I'm like, maybe with some more Google foo, now I know that this thing is an AC1052, I can find something. And I actually didn't find anything, but I did find a Chinese blogger who posted a bunch of posts on how to work with this SDK. And even if you can't read this, even if you can't read Chinese, you can probably understand that there was some frustration involved there. I don't need to translate this, you probably recognize this. But one of the things there was that he posted a bunch of screenshots, and in there it showed that the AC calls itself the SDK_AC109N. So I've got something new to Google for. And yes, I got lucky. After some Googling, I actually found a copy of the SDK in the hive of scum and villainy on the backwards bits of the internet that's called GitHub. Yeah, it was just out there on GitHub. So great, we downloaded, and I'll spare you the details. I'll just give you a summary. So the good parts of the SDK is that we actually found some code that matches the binary. So this is certainly in the same family of our chip. The SDK has some hardware register definitions. It also has some peripheral drivers, although they're not that useful because I2C, yeah, I don't care about that. And it has some hardware docs. They're obviously in Chinese and they're very sparse, but they're there. So the bad thing is that we can't really make our own firmware because this uses a proprietary Keel compiler. It doesn't help us reverse engineer the chip that much either, because most of the logic is in binary blobs that just get linked into your thing. The audio hardware is entirely undocumented. You're supposed to use those binary blobs to talk to it. Unfortunately, there's also some things that I really wanted in there. So first of all, I would like to, apologies. I would like to have some mention of the F1A format, because, you know, in the end, that's what we're trying to do. We're trying to encode our own F1As and replace the music in those things. This thing doesn't mention it. Some peripheral registers actually seem inaccurate even in the examples. They're writing to registers that are not supposed to be GPIOs when they write to GPIOs. I'm not entirely sure what's going on there. So there's no banking or encryption info. Luckily, we don't need that. We already figured that out all by ourselves. And the peripherals don't match our chip. And that's a bit of a problem, because it would be great if we could just write to peripherals and know what that was going to do. But there seems to be some sort of mismatch. There's some overlap as well, but not everything. So the SDK and knowing that this is the family we need to look at did actually help us, because someone else also did their own squirreling. So peripherals don't match the chip. Sorry, I'm looking at the preview. So someone else also did some squirreling, and they found another product by Geely, which is the AD140. And I have no idea what that is, but it does come with a tool to do audio conversion. It's in Chinese, obviously. It's Windows only, obviously. But the idea is that you can put a bunch of waves or MP3s or whatever in there. You select the format you want to encode it into, and it supports F1A. And you press OK, and it just does the thing, which is great. Obviously, we also looked at what this did a little bit, because we're now very curious what that F1A format is. There was a lot of speculation about ADPCM and AAC and maybe an MP3 thing. Well, actually, it turns out it's the WMA, Windows Media Audio. Who'd have thunk? So what happens is that the thing is a pipeline that converts it to a low bitrate Windows Media Audio file, and it then strips all the metadata of the Windows Media Audio file, only keeping the bare bones data, and that's your F1A file. So that means that we now have something that can encode F1As, which means that we can replace the songs, which is absolutely great, because I can show you this. Yeah, you should see me again. So I now have one of the Buddah machines that produces something way more relaxing than Chinese chants. And I'll cut it off there before, you know, YouTube does content matching shenanigans. So yeah, that's great. We can replace songs. Fix the encryption. We can replace an F1A. We can repack and re-encrypt the thing. And yeah, now the music that's in there is all ours. Great. Now what? So yeah, we have an encryptor and decryptor. We have some information about the SoC, but some of it is incorrect, and we know what the F1A is. So what can we do with that? What do we want to do with that? Well, we could make an open source encoder, but WMA is proprietary and very undocumented. There's no low bitrate open source encoder out there. FFmpeg can only do high bitrate things, and we don't entirely understand the format yet. So maybe we should make an open source SDK, but well, you've probably seen what I think about the architecture. It would need way more reverse engineering, and you can't obtain the chip anyway. So yeah. So does that mean that you know, we just call it a day and we chuck away the thing? I wasn't really feeling like that either. It's probably better to you know, reuse it. And actually, someone posted a few weeks before the con something really nice, namely a design to make your own Remoticon 2 badge, and it came in the form of a KiCad file that you could just put your own schematics in. So I did. I replicated the schematic in the Buddah flower, added some LEDs, and you know, sent it off to be made. Unfortunately, it's green. I'd rather have it be in like purple or blue, but I had the choice between green or way too late for the con. So yeah, that was an easy choice. And this is what it looks like and does. So you may have already seen it. This is the thing. And if you turn it on, it plays the theme of the Remoticon, and the LEDs you see there, they actually output the values that are generated by the LFSR that encrypts that decrypts the flash. So what was once secret is now happily blinked out. So that's great. And with that, with my nice memento of this year's Remoticon, my talk ends. I'd like to thank all the people who came along in this journey. As I said, this is not something that I did. This is something that a whole bunch of people did on YouTube and on the subreddit. These are all the people that really helped. If your name is in there, I really hope to do a project like this with you again. And then all that remains is to thank everyone for listening and for watching. And that was my talk.
Wow. Yeah, I mean, that's the kind of stuff that got me interested in Hackaday in the first place all those years ago. It's exactly the kind of stuff that I used to like to read in articles, and hearing about it now in person, that was awesome.
It's really fun to do as well.
It looks like a blast.
The people here, the mistake that they made with the encryption is that they actually made it fun to break, and they should never do that.
You're hanging red meat in front of people like you when you do
For
stuff
sure.
like that. Yeah, so everybody wants to clap, so I'll clap for you.